Alright guys, here we go with chapter 6. So this is titled as a weak acid or a weak base, meaning it will be a similar process whether you're dealing with the weak acid or the weak base, okay? Those are your practice problems. I'm sorry about the formatting. This should be NH3. This is NH4 plus, H plus, OH minus, okay? We found out if the solution is acidic, basic, or neutral, and I give you a volume and a molarity of NH3, and I also give you the Ka value, 5.7 times 10 to the negative 10. Okay, I know the formatting is kind of funky. You'll be fine. Okay, first things first. Identify the major species. Okay, it is ammonia. Okay, that's not the important part. The important part is, what is ammonia? Ammonia is a weak base, okay? That is the major part of identification, a weak base, okay? Knowing what weak bases do and how they act is what will determine how we go about solving this problem, okay? So, write out the reaction. Well, a weak base, and of course, I'm going to do it the long way, okay? It's easier to see. I'm going to add it to water, okay? It's a little bit better to see when you do that. I skipped this when I did the acid problem. You can also do it with the acid problem. There's no reason that you can't, where the acid loses the hydrogen and the water gains it. Bases are easier to see if you actually add them to water as opposed to just writing ammonia. Now, very important, this is equilibrium. Why? Because it's weak. Weak substances go to equilibrium. They do not go to completion. So the Bronsted-Lowry definition of a weak base is, weak bases are hydrogen ion acceptors. So the ammonia will turn into NH4+. This guy took in a hydrogen. Okay, well, who did it take it from? Well, the water. Now, try to think of water as HOH. If the water loses the hydrogen to ammonia, what's left? Well, OH minus is what's left. Okay, so this is the equilibrium of ammonia in water. Solution is really what it means, in solution. Okay, so we write out an equilibrium expression. Well, Kb equals products. So NH4 plus and OH minus divided by reactants is NH3. Why don't I include water in there? Well, because it's a liquid, okay? You never have liquids in here. You either have aqueous or gases, okay? So products over reactants. And everything is 1 to 1 to 1, okay? Why did I call this B again? Well, because this is a base. It's equilibrium constant of a base, okay? And K is given. Ooh, look at that. That's a mess up. Oh, no, it's not. I lied. That's not a mess up, okay? I call this KB, okay? So now, anytime, if you remember back in the equilibrium chapter, when K is given, you're not solving for it, it's given. Almost always you have to let X equal something. So I'm going to set up my ice chart. NH3. I'm going to omit the water for now. Why? Because it doesn't matter in terms of your expression. I'm just going to write what everything else is, all right? Okay, ICE. In one of our last problems, I had you do a dilution because I gave you a volume, a molarity, and a new volume, so you had to do a dilution. I did not dilute this. I have a volume of it, and here's its molarity. The volume pretty much is irrelevant in terms of mathematical. In this problem, it's useless. All you need is the molarity. It's 0.2 molar NH3, and you assume that's your starting or initial molarity, okay? 0.20, sorry about that, molar. And you should have no product at the beginning, okay? Down here, we will let X equal. Who do you want it to equal? Ammonium or hydroxide? Oh, ammonium, you say? Okay. At equilibrium. So ammonium is going to be X, which means I must have gained X here. If I didn't have any to begin with, and that's what I ended up with, well, ammonium and hydroxide are on a 1-to-1 ratio, so that's plus X there. Okay, ammonium and ammonia are also in a 1-to-1 ratio, so that's also X. But remember, reactants lose concentration. Okay, so this is what we have for equilibrium. Okay, so we have all of these equilibrium values. Some aren't really values yet, they're variables. So give me a second. Okay, we are going to plug back into the equilibrium expression. All right, so KB equals, my two products were X's, and the bottom was 0.20 minus X. Okay, now the next thing we do is we try to get rid of this guy because it makes our life easier. So we're going to assume, and this will always work for the sake of any test you take in here and or the AP test, that X is much, much smaller than the number it's being subtracted from, which in this case is 0.2. Pretty much we're trying to say it's negligible. So it's so small that when you subtract it from 0.2, it doesn't change 0.2 very much. So you say bye-bye to the X. Makes it go away right there. Okay? Now something that we have not gone over yet is this. KB Ka equals Kw. Okay? This is on your equation sheet. What that means is if you know two of the three constants, you can find the other, and you should always know Kw because it is 1.0 times 10 to the negative 14th. Okay? And then Kb times, what was the Ka? Oh, I have to pull it back up down here. Let's see. The Ka was 5.7 times 10 to the negative 10. Sorry, I'll go back now. 5.7 times 10 to the negative 10. You will solve for Kb. That's what has to go there. So let me whip out my calculator. And 1 times 10 to the negative 14th divided by 5.7 times 10 to the negative 10. And I get Kb is 1.75 times 10, 1, 2, 3, 4, 5, to the negative 5th. So 1.75 times 10 to the negative 5th equals x squared over 0.20. Multiply both sides by 0.20. Then take the square root. I am not doing all of that for you. I know you can do that. So 1.75 times 10 to the negative 5th times 0.2 square root. I am getting x equal to 0.00187 molar. Okay, so now you got to go back to, well, what is X? X is the hydroxide ion concentration is 0.00187. X is also the ammonium ion concentration. Okay. Remember, ammonia is 0.2 minus X. Does that change it? I think it does a little bit. So let's try 0.2 minus X. And it does. It changes it to, not much though, but it does change it to 0.1, sorry about the 0.98 molar. Okay, concentration. All right, we're partway there. There are alternate ways now to end up with H plus concentration, and then with pH and POH. There's many different routes you can take. Here's the way I'm going to take. I'm going to find POH off the bat. If you haven't noticed yet, there's an equation on your equation sheet for POH instead of pH. It is opposite the log of OH is POH. Okay? So the POH is opposite the log of 0.00187. So let me get my calculator out. By the way, my calculator is my phone right now, so that's why it's taking me so long to do these. So 0.00187, opposite the log. POH is 2.7. Ooh, how many sig figs? I think we're doing 3 sig figs. 2.728. 3 sig figs. So what's the pH? Well, you take 14 minus the POH to get the pH. Okay? And the pH is 11.272. That is really nice. Is that a basic pH? It sure is. Ammonia is a base, so we're seeing a basic pH. Okay? How do you get hydrogen ion concentration? Well, remember H plus. This is one of the ways you can do it. There's actually another way, which we'll go over at a later time. H times OH is 1 times 10 to the negative 14th. So if you plug your OH in right here, sorry, I'm running out of room. H plus times 0.00187 equals 1 times 10 to the negative 14th. You rearrange, so you take 1 times 10 to the negative 14th, and you divide. So 1 times 10 to the negative 14th divided by 0.00187. I'm getting my H plus concentration. I'm going to do it up here because I ran out of room, okay? To be 5.35 times 10. Ooh, I got to count. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. I got 10 to the negative 12th molar. All right, so I've got my OH, I've got my ammonium, I've got my ammonia, I've got my POH, I've got my pH, and I've got my H plus concentration. That is how very similarly you would solve were it a weak acid. Okay, and that is the end for a weak acid or a weak base type problem.